Throughout our study of statistical inference, we will repeatedly encounter the normal distribution. But why is it so important and helpful? The answer can be found in the Central Limit Theorem, which is one of the theoretical cornerstones of statistics. This video accompanies open intro statistics and examining the Central Limit Theorem. We will begin with an informal definition of the Central Limit Theorem, and then we will see how it relates to a few examples. The normal model for the sample mean tends to be very good when the sample consists of at least 30 independent observations and the population data are not strongly skewed. The Central Limit Theorem provides the theory and says informally, the distribution of the sample average is approximately normal. The approximation can be poor if the sample size is small, but it improves with larger sizes. Let's consider the Central Limit Theorem in the context of three different population distributions. The uniform distribution is symmetric. The exponential distribution may be considered as having moderate skew since its right tail is relatively short, with few outliers. And the log normal distribution is strongly skewed and will tend to produce more outliers. Each of the distributions shown here have a mean of 1 and a standard deviation of 1. Now consider the sampling distribution when we take samples of size 2 from each of these populations. The left panel represents the sampling distribution of the sample mean of 2 observations from the uniform distribution directly above. The dashed line represents the closest approximation of the normal distribution. Similarly, the center and right panels display the respective distributions of the sample average for data from the exponential and log normal distributions. We can see the sampling distribution for the exponential is not very normal, and the contrast is even more apparent for the log normal population distribution. With such a small sample size, the sampling distribution tends to be similar to the population distribution. However, as the sample size increases, the sampling distribution becomes more normal. As we look through these results for larger sample sizes, focus on two things. First, watch the sampling distributions begin to look more normal. And second, notice that the distributions are becoming narrower, which will be seen by the narrower scale on the horizontal axis. Here are the sampling distributions when we take samples of size 5, 12, and 30. Watch the sampling distributions get closer to the normal model as the sample size increases. Before we conclude this video, let's see this transformation one more time. However, this time, we hold the x-axis steady and watch from a distance as the sampling distributions become more narrow. Here are the results, just like we saw them before when the sampling distribution is based on samples of size 2. And here are the same results holding the x-axis steady for samples of size 5, 12, and 30. Notice, it is a little more difficult to see the sampling distributions become normal, but it is much easier to see how narrow the sampling distribution becomes as the sample size increases. This video gave us an informal introduction to the Central Limit Theorem and showed us examples in a few different settings, including different sample sizes and different underlying population distributions. If you learned something you found interesting, share this video with a friend and visit openintro.org for more resources.